Okay, so I'm going to talk about education, and most of the other speakers have talked of either parallel and distributed computing or only parallel computing. So I'm going to talk of only distributed computing. I have some ideas about how threads can be taught in CS2. That's not what I will talk about. Okay, and what's the problem I'm trying to solve? The same problem that Sushil mentioned, that his group tried to solve snowed in a hotel. And I'm trying to do it alone, and there's pros and cons there. But the problem is that today's undergraduate curriculum has many courses, and you see some of them here, and none of them is distributed computing. Yet each of these courses can extend naturally to distributed computing. And one way to solve the problem is to actually teach a course of distributed operating system, distributed database system, distributed algorithms, and that's what you do in graduate courses. So what if you want to have a course at the undergraduate level, and I'm saying a course because we can't afford 5 courses, that teaches distributed computing. Okay, so that was the problem that I've been addressing. And what's the answer? Well, you have to go back to these courses and say which one of the more fundamental. And I think we'll agree that data structures and algorithms is fundamental. We'll agree that systems is fundamental. And what do we mean by systems? We mean abstractions. Whether it's loops or threads, it's system abstractions, and both how they are used and how they're implemented. Okay? So when you go to the distributed, and so those are the 2 themes we'll take, and we'll talk about how to make that distributed. And on the right, I've described what that exactly means, and there's not enough time to talk about that. But very quickly, abstractions becomes IPC, inter-process communication. And by IPC, I don't mean just low-level message passing. I do mean low-level message passing. So Java NIO is what is used in scalable servers. But I also mean high-level RPC, where things are taken care for you, and lots of layers in between. And what does algorithms become in the distributed case? A friend from Botswana said that there are 11 algorithms in this world. I think the main fundamental algorithm in distributed computing is consistency. That takes many forms, and you see some of those forms there. But we can talk about various guarantees we give and the performance implication they have when we talk of consistency. So this course then becomes a systems and algorithms course, which is kind of tricky to do. And what's even trickier is to make a project around it. And why is a project good? If you're going to teach it to undergraduate students, they should be able to put their hands on something and have it concrete. And we heard today the merits of doing holistic teaching. And so this is where the advantage of being alone is good, because you can craft a project that has these layers integrated with each other. And so that's what I've done. And let me quickly, since I do have a couple of minutes left, talk about the various layers. So you have to run your distributed programs on some platform, and you can do it on any cloud platform. A distributed program can run on a single computer or any cloud. And the ones that my students use is an NSF project, it's a funded project called Cyverse. At the top is a distributed simulation. And there was some discussion that, where should distributed computing be done, which should be done in CS2. In my CS2 course, students built non-distributed programs, and in this distributed course, they take that non-distributed program that they or somebody else built in CS2 and make that distributed. Okay? And they don't just make it distributed; they make it distributed with guarantees, various levels of guarantees, and those guarantees are determined by the algorithms you see on the right. So there's just regular broadcast, hoping everything will go well. There's atomic broadcast, two-phase commit, and Paxos, which is the most fancy algorithm for distributed computing that's used in Oracle and Amazon and other data centers. So they get to play around with all of them. Paxos, they just play around with. The other algorithms, they actually implement. Okay, but they're simple enough to do so. And not only do they implement, they also go and measure the performance on a cyber infrastructure. And in terms of IPC, I said there's asynchronous message passing at the bottom and RPC at the top. And there's layers in between, but those are not customizable in commercial systems. So I've actually built a stack myself, which is in the spirit of educational operating systems, that they use to change aspects of the implementation. So since they're doing implementations, the question is, how do they submit their work and how is it graded? And you can't just expect them to sort of give the code and us to test them. We want them to be able to actually run it in the cyber infrastructure. We want them to be able to show race conditions, the kind of stuff that you talked about that could happen to asynchrony. So what this simulation that I have is visual, and in terms of visually, you can see lack of consistency and consistency, and consistency and inconsistency and consistency. And I'm 30 seconds up. They also go in, so they actually produce videos with these demonstrations, and these are all, the projects are all page. So the summary is that a distributed course can do both design and implementation of algorithms and abstractions, and IPC and consistency are the two themes there. And you need a very carefully crafted project that holistically shows them coming together. And this goes together with video demonstrations and projects. And I'll finish my 5 minutes here.
Thanks a lot.